Hello, this is Carl Nielsen, and this is my oral presentation for assessment number 3, Match the Phase Portrait. So let's just get right into it. Ooh, hold on. There we go. So this right here is just a way I rewrote the format that we were given for the system of differential equations. I just rewrote it in matrix form to make it a bit easier. Here it is expanded out, and here it is abbreviated. So getting right into it with figure 1. So our task 1, we just had to find a system of differential equations that match this phase portrait. So first thing I did is think about kind of back to linear algebra, the null space. So I saw this line about here, which is about y equals 1 half or negative 1 half x. I was thinking about that. I'm like, that's got to be like a null space for something. Um, So I'll just try that to start out with. We'll see if it goes anywhere. So boom, null space is given by the span of that vector. That vector is just the same slope as that line that I was given, or that I gave. Um, I was trying to find a certain matrix A that would fit this, but it's hard because there weren't any multiples of 2 that we were given. We were just given 1, 3, 7, and 0. I didn't want to use 0 yet because we could only use that in one of the portraits. So I'm like, I'll just take the next best thing and I'll take 7 and 3 because those are about like half and double of each other. So I just did that. Um, and that worked for this one line. This is our red line. But I also noticed that we have another null line given by this blue line. And this is going to be where our vertical lines are going to be. So where there's no change in x. So knowing these two lines, I estimated this blue line to be about y equals negative x. So we get this, a y null line at about 7y equals negative 3x, and an x null line at about y equals negative x. And about is the best I'm going to do with these phase portraits because we can't like perfectly measure everything with them. So I'll just take that and then I tried graphing it and it looked very close. So I just said, I'll go with that. I rearranged it this way. This makes it easy to write our system because right here and right here, these are like the right side of our differential equations. And right here and here, this is like our left side because this is where the slope is going to be 0 for our x or our y. So we can just input our differentials for that, and we get dr over dx, or dx over dt equals x plus y, and dy over dt equals 3x plus 7y. Again, I tried plugging this into different plotters, and it looked good. It looked like it matched it pretty well. So I decided to start solving it. I used the eigenvalue method for the first part, so I'm taking the determinant of our matrix minus the identity matrix multiplied by our eigenvalue, or by lambda. And for that, this is what we get for our eigenvalues right there, 4 plus or minus 2 root 3. And then I was like, it's going to be difficult trying to find the eigenvectors from that, so I'll just use the A method to get the eigenvectors. This is the value I got for A, and then plugging A back into that equation, we can get our eigenvectors, which we get as these two right here. And then we can kind of just like check which eigenvectors are going to go with which eigenvalues. It's just two different combinations, so it's a lot easier to check than, a whole bunch of different things. And this ended up being the correct combination right there. So this is going to be our general solution right there. We have e to the power of our eigenvalue right here times by t, same eigenvalue right there. And then again, these two are going to be our eigenvectors. Sweet, so that's how I solved problem 1. This is just a plot of it with 2 points we see our initial value starting here, it shoots off up top, initial value starting here, it shoots off down below. And if we were going to be on like this line, we'd like shoot that way. And of course, starting at the origin, we're just going to stay there. So there was figure 1. Figure 2, I did the same sort of thing, trying to find null clines. So I noticed right here we have like horizontal lines at these 2 points, and we also have like vertical lines at these points, right? And we can connect all those with lines right there. These are the null clines that I got for that. These are the lines, or the lines that I found for that. Just estimating it using the numbers that we were given. So there we go, and pretty simply, just like the other one, that's how we get our differential or system of differential equations. Boom, boom, boom. I use the eigenvalue method to find our eigenvalues, of course. This is what I got for them, plus or minus square root of 46. And then again, I use the A method to find our eigenvectors. This is what I got for those, our values of A, meaning I got these for our eigenvectors. And then again, plugging those in, checking, making sure they were matched up correctly. This is our general solution. And again, we have eigenvalues and eigenvectors right there. And then finally, here's the plot that I made for that one. It looks like it matches very closely, and if we like plot a few different points, we can see the behavior that it has. This one's going to 0 because I inputted a 0 value for C2 and a non-zero value for C1. So then we only get the decay part. And then this one's dropping down and then shooting off. So for the next two, the way I like to think about them is kind of going back to linear algebra and thinking of matrices as linear transformations. I knew there were I know there was a certain matrix for rotation. So I was like, okay, I'm gonna try and take like our identity matrix and see how I could rotate that to get our next two plots, our next two phase portraits. So here I just wrote what the system would look like with our identity matrix. We just have the change in x is given by x and the change in y is given by y. And this is what that looks like plotting. So, all right, we have this, and then we go to the next one. And I was like thinking, okay, how can we get from this to this? And if you look at it and you take every single vector and you just rotate it by 90 degrees anywhere along this point, we're going to get this. So we get this expanding outwards and we turn it into this circular by just rotating by 90 degrees. And I also remember that there is a rotation matrix given by this, where you have cosine and sine, and theta is our angle that we want to rotate by. So I just input the angle that I wanted to rotate by. It was 90 degrees. And that gives us this as our final, or our matrix. And then plugging this back into the format that I made earlier, we just get this as our system of differential equations, where dx over dt is negative y. I guess we really have a 0x in here and a 0y. So that's why I was using the zeros. These are just ones. So knowing that as our system, I just use the A method of finding our solution, because we're going to be getting a complex solution. So finding the eigenvalues is going to be a bit more difficult. I don't want to have to deal with that. So I just did the A. This is what I got for the value of A, which means that we're going to get e to the I t plus or minus in our solution. And we also know that that is going to be cosine of t plus I sine of t we of course can just ignore the sign. So it's going to be cosine plus or minus sine of t. So yeah, that's what I did. I just did that. We have these two are going to be 1, and then these two are going to be the second solution. So those are our two solutions right there, and then we can just combine them to get this one solution for just x of t. And then knowing this, or knowing these equations, we could just, oop, that was bad. Integrate by dt on each side. And then we could see that our y, we're just going to get just y for that, is going to be equal to the integral of our x. So knowing that, I just took my x, I integrated it, and then that's how I got that y. Simple as that. Plotting this, we get circular patterns. Anywhere we start, we're just going to be going in a circle around, counterclockwise, very simple. No growth, no shrinking, just going in a circle. So that's what I got for that third one. And finally for the fourth one, I just thought, okay, this just looks like a rotation, but only by like maybe 20 degrees. So again, using the rotation matrix, I found the closest match to getting that about 20 degrees, where this was about double of that. And boom, that's what I got for the final system. I decided not to solve this one, but if we plot this, this is what it looks like. So we can see that it's very similar, and again, we would follow that. Bada bing, bada boom, works out. So that's what I did for my assessment number 3. That's how I solved it. The thought process I kind of went through, and some graphics to go along with it. Thank you.